Hello, my name is Alex Gertz, and this is my final project presentation for MEMS 5001 Optimization Methods in Engineering. My project is a center pole brake arm assembly which has been repeatedly failing in service. This is taken from the 4th edition of Robert Norton's Machine Design. So my goal is to use topology optimization to redesign the brake arm of this assembly. Most topology optimization software, including what I use for this project, uses the finite element method to perform analysis on the given system. Once the initial optimization has been completed and a rough geometry has been produced, that shape then must be converted into a smooth and continuous shape, which can be more realistically manufactured and further analyzed. In the program I use, that is accomplished with polyNURBS, which is basically a way of quickly creating freeform solid geometry. Some of the pros of topology optimization are that it minimizes the amount of material needed to achieve required strength, which reduces the cost of the part, and it also reduces production time. Some of the cons of topology optimization are that the parts it spits out are often difficult to manufacture, and they're usually only feasible with additive manufacturing. So most of the free body diagram work was done for me by the book, but here are the results. So if we assume that the force applied by the cable is 1046 newtons and the coefficient of friction between the brake pad and the wheel rim is 0.45, then the frictional force of the brake pad against the wheel is 587 newtons. Now applying the results of the free body diagram to the model, the cable force pulls at a 34-degree angle counterclockwise from vertical, and the frictional force is applied to the brake pad in the z direction, which is coming out of the page as shown. Here we see the dimensions of the original part, which we will use to compare to the optimized later on. Some of the initial analysis results are shown here. This is the displacement and factor of safety. And here is the von Mises stress and tension and compression. Since the textbook did not specify how the part was failing, the primary goals were simply to increase the factor of safety and decrease the maximum displacement. And the secondary goals are to decrease weight and decrease the von Mises stress, which is related to tension and compression. To allow the optimization process to guide the shape of the brake arm, I created a new part to use as the design space. This part was much bigger in all areas, particularly in the semicircle section where the factor of safety was shown to be the lowest in the initial analysis, and also increased the thickness from 15 millimeters to 40 millimeters so that the shape of the part in the z direction could be optimized to counter the force of friction on the brake pad if needed. After optimization and applying polyNURBS, here are the results of the geometry. It is clear that most of the interesting geometry is in the XY plane, shown in the top left, but you can also see some stuff going on in the bottom right, countering the frictional force. After completing optimization, I performed the same analysis that I had on the original part, so here are the results of the displacement and factor of safety analysis. And here's the results of the von Mises stress and tension and compression. When comparing the analysis of the optimized brake arm to the original, we can see that the mass, displacement, and factor of safety were all improved. However, the maximum compression and tension of the original was actually better in the original, so let's take a closer look at where that is in the optimized to see what's going on. So here we can see that the maximum tension and compression is right where the brake pad attaches to the brake arm. So because of this, I'm not concerned at this result, since if this was actually being produced, additional material would likely need to be added to allow for bolts to attach the brake pad to the arm. So in conclusion, using topology optimization, I was able to decrease the mass of the brake arm while also decreasing the maximum displacement and increasing the factor of safety. And while I was not able to achieve my secondary goals of decreasing the maximum tension and compression, as we just discussed, additional material would likely need to be added to that location anyway to allow for bolts to be applied. So I would call this a successful use of topology optimization. Thank you.